Hello, I'm Dave Brown for Teletrain, and today we're going to discuss brakes and clutches. Now, we'll cover the brakes first since they are usually simpler in operation than our clutches, though both operate on the same basic principle. Now, what is a brake? It's a mechanism used to stop something in motion. For example, if we wanted to hold a machine in a stopped position to prevent it from moving. Also, it may be used to limit motion. For example, where we would want to hold a constant speed on a unit, such as a roll of wrapping material. Here, it would be used to keep the roll from overspeeding. This is probably the simplest type of brake. It's called a drag brake. Now, this may be either a band or a block. Here is a band type where we have a weight hanging on a leather strap, which in turn slides on the face of this drum or pulley. Or we could have a drag block type where we would hang a weight on a lever, as you see in this sketch, and a friction material here would slide on the drum as it turns. Now, this is the drag block type. One place you may have seen this type of brake is on TV or in the movies. In the old westerns, the early settlers are shown using block-type drag brakes on their wagons. It was used to slow the wagon as it went down a hill. Here they were converting energy of motion, that is the motion of the wagon, into heat energy, the heat on the face of the brake. The same basic idea is used in all brakes. That is, some method is used to absorb energy of motion and change it into energy in the form of heat. Therefore, one of the limiting factors on brakes, and something that usually must be taken into consideration when calculating size, is the brake's heat dissipating capacity. This capacity to get rid of heat limits the frequency of operation. For example, a brake which is operated 50 times a minute may have to be several sizes larger than would be required to handle the same load operating only once every hour or so. Now, this is true because of the heat buildup. With each stop, energy is absorbed in the form of heat, and unless there is some way to dissipate this heat, the brake will get too hot. We've looked at the drag brake. Now let's look at the various other type of brakes. First, there is a block brake. As you can see, this is nothing more than a block of friction material which is pressed on each side of a drum and stops the drum from rotating. When we press this handle this way, these two brake pads are moved into contact with the drum to stop it from turning. The friction material is usually some asbestos compound, or at least some material with a relatively high coefficient of friction and a high heat resistance. It may be a woven material, as we see here, or a cast material, as we see here. Now, here's how the block brake looks when an electric coil, right here, is used to operate it. This type of brake is frequently used for heavy-duty applications such as overhead cranes. In this case, as you can see, the coil pulls the plate over, which compresses the spring and releases the brake. When the current goes off, the spring actuates the brake. This unit is also sometimes called an external drum brake for obvious reasons. The band brake utilizes the same basic principle, except it has a band which wraps around, as you can see, completely around the drum, and this allows more friction surface. This unit has a flexible steel band to which a friction surface is attached. By moving this lever up, we tighten the band, which in turn applies a braking force to the drum. The force to actuate either of these brakes may be in the form of an electrical magnetic coil, an air or hydraulic cylinder, a spring, or manual. Next comes the caliper disc brake. In this type of brake, we have a metal disc, like this, which is mounted on the shaft we wish to stop. We apply a friction surface to both sides with this unit, which is called a caliper. Here are the friction pads. This allows us to stop the disc, much as if you had a pair of pliers and grab the disc. Pistons, located here and here, force the friction surface in against the disc. And these may be operated by either air or hydraulic pressure. The capacity may be doubled by simply using two calipers on one disc. This type of disc in recent years has been used on automobiles quite successfully. The disc may be either a single ring cut from a plate like this, which you will note has cooling fins right here, or it may be a double disc, as we see here. The double disc type allows air to circulate between the two faces, and this further helps to cool the unit. In recent years, the disc type brake has been used quite extensively on automobiles, especially on front wheels. Next, there's the internal drum brake. And by the way, this is the other type that is used on automobiles. This is the brake that was used almost exclusively on automobiles up until some 10 or 12 years ago when the caliper disc was introduced. This brake also has a number of industrial applications. In this case, we have friction pads, or brake bands as they're frequently called, which are forced against the inside of the drum here by these cylinders, here and here. This type is usually hydraulically operated. Next comes the disc type brake. In its simplest form, as you can see from the sketch, we have a disc here to which pressure is applied by a friction disc here. Now this may be, as you can see here on this actual brake, only one disc and one friction surface, or it may be multiple discs and multiple friction surfaces like this. If it is multiple disc, we tend to compound the problem of heat dissipation. However, we do get a very high braking capacity in a small area because we have a large friction surface. If, however, the stops are infrequent and space is at all a problem, the multiple disc unit is usually a good choice. In certain applications where there is constant slip, such as on a drag brake type, the unit may be cooled by circulating water through special cooling circuits cast right in the housing. The disc brake, either single or multiple, is one of the more commonly used brakes. It may be actuated manually, with air, by hydraulics, or electric coil. If air is used as the actuating force, it has one advantage in that we can get a varying braking pressure by merely varying the pressure of the air we apply to the unit. This is done with a simple pressure regulating valve on the air pressure. By putting a bleeder valve in the air line, we can make the brake engage just as slowly or as rapidly as we desire. Many units that operate with air may also be operated hydraulically. However, care must be exercised so we don't exceed the pressure the unit was designed to operate with. Most air-operated units are built for a maximum pressure of 150 to 200 pounds, while hydraulic brake systems frequently are designed for pressures up to 1,000 pounds per square inch or even more. Electromagnetic brakes are most frequently used on applications like electric motors. But in most cases, these are spring set. So we use an electrical magnet here to release the brake and a spring to apply the actuating force. This type brake is also used as a safety brake, since the spring automatically applies the brake if there's a power failure. Electromagnets will be explained later in the tape. One thing we should always remember with a brake The drum or surface the friction pad is applied to should be a polished surface, because if it's a rough finish, it can reduce the capacity of the brake by as much as 50%. Now let's discuss clutches. Clutches are very similar to brakes, except that here, instead of stopping some mechanism, normally we are connecting or disconnecting some mechanism to or from its drive. Now let me reword that. Clutches are used as a method of connecting or disconnecting a powertrain. A powertrain is the flow of power that goes from some machine to a piece of equipment which we desire to drive. The reason for having a clutch is usually to allow the motor to run continuously and just stop and start the load by connecting and disconnecting the powertrain. Usually it's two shafts that we are connecting or disconnecting. First, let's look at simple clutches. The simplest type of clutch would be the jaw clutch. This, as you can see, is connected by moving this jaw into this jaw. Now the next step in our evolution from the jaw clutch is the spiral jaw. The spiral jaw will drive only in one direction. If the drive reverses, the clutch will automatically disengage. As you can see, this is the movable jaw which slides in and out on this keyway. It is moved by pushing on this part here, which is called a yoke. Although this cut doesn't show it very clearly, this is not one continuous shaft, but is cut in two right here, and this one is cut right here. These two style clutches are only clutched in when both the motor and the driven machine are stopped. Otherwise, the shock would be terrific. Next, we have safety or slip clutches. As you can see, this unit basically consists of nothing more than two friction surfaces and a metal disc which are forced together. Now here we have a disc spring. As you can see, this is a type of cone-shaped spring. Now we assemble the unit like this. Pressure plate first, that's this unit here, then a friction pad, now the disc. The disc is usually a sprocket which has had both sides ground to get a smooth finish. Now we put on the other friction pad, pressure plate, the disc spring, the disc spring follower, and finally a nut to tighten them up. Now by tightening or loosening the nut, we can vary the point at which the disc will slip. When the amount of torque which the unit is able to transmit is exceeded, the unit slips. If you'll remember from the other tapes, torque is the twisting force in a shaft. This unit allows us to have a predetermined amount of torque designed into a system which prevents overloads. If a potential overload does occur, as in the case of a jammed conveyor, once the system is freed, this type slip clutch will once again start carrying the normal load and usually will do so without any additional adjustment. This unit will work equally well rotating in either direction. Next, we have the ratchet clutch. This is a clutch which allows movement in this direction, but engages when movement is attempted in the other direction. Actually, these could be called a type of brake, but since the term clutch is normally applied, we will look at them in our clutch series. These are also called backstops and are normally used on items such as elevators or conveyors to prevent them from running backwards. Let's take the case of an inclined conveyor that is fully loaded. If the current fails or the powertrain breaks, the material on the belt or in the elevator would then run back and pile up at the base of the unit. Now, this could cause some real problems. If, for example, the conveyor had several tons of sand on it, so normally these units are installed with a ratchet clutch, which prevents them from running backwards no matter what. Ratchet clutches use some type of pawl or ratchet arm, and the term ratchet means it moves in and out. This little part right here is called a ratchet. We normally have a spring right here to hold pressure on the ratchet, but there are several patented arrangements for holding the ratchet arm back so that it doesn't bounce in and out with every tooth, but still does make positive contact when the unit starts to move backwards. One disadvantage to this particular unit, as you see, the distance between engagement of the teeth is relatively great. So this means that there is an appreciable amount of movement backwards before the unit does stop moving in the back direction. If a quicker stopping is required, then normally different styles are used, which are called roller and cam clutches. Now you'll notice movement is allowed in one direction, but it will not move in the reverse direction. The roller clutch uses a roller on an inclined plane which engages this ring. The ring is called an outer race, same as in bearings. As you can see, we have a spring pushing behind the roller, and as long as the unit moves in this direction, the ball keeps pressure on the spring and free movement is allowed. But when we change and try to go in the opposite direction, the spring pushes the ball out along this inclined surface. This locks the inner race to the outer race. These rollers are evenly spaced all around the inner circumference of the outer race. Another method of doing the same thing is with what is called either cams or sprags, depending on the manufacturer. These cams are made so that this X dimension from here to here is less than this Y dimension from here to here. Now here's a little clearer illustration. This allows free movement in one direction, but when we go in the other direction, the cam rocks back like this and fills up the space here, locking the inner race to the outer race. This spring here holds a constant light pressure on the cams to hold them up in position, ready to lock with very little back motion. Next, we have the fluid clutch. The fluid clutch transmits power from one shaft to another by a fluid medium in between. This is best demonstrated by a regular fan, as you see here. Now we have the fan sitting here, and we've put this toy windmill that we've made in front of it. When we start the fan, the windmill starts to turn. This is because air, in this case, is the fluid, and we are actually transmitting power from here to here through this simple fluid clutch. If we encase both the fan and the windmill and put oil in as the medium instead of air, we're able to transmit even more power. Now, if we want to do an even more effective job, we take the blades off the fan and turn them so they are parallel to each other. We pull them up close together, where there's only a fraction of an inch in between, and put oil in as a medium. If we encase it, we have a commercial fluid clutch. Since the input impeller here and the output rotor here actually never touch, there is a smooth flow of power, and very little shock is transmitted between the input and the output shafts. There's another method of using the same basic type of idea, except in this instance we use steel shot. Steel shot, as you see here, are small steel balls. Now we encase this shot in a housing, as you see here. As the housing spins, the centrifugal force, or force to the outer edge caused by the spinning, slings the shot to the outside. It's packed tighter and tighter against a rotor here, as the speed of the housing increases. Finally, the rotor begins to turn with the load and continues to carry it until the housing, which holds the shot, is slowed down. Another clutch which uses the centrifugal principle is called, logically enough, the centrifugal clutch. In this case, it's the inner rotor which is connected to the power source. As you can see, the friction pads, the green units here, are held in place with these small springs until the rotor gets up to some point less than top speed. At this point, the centrifugal force overcomes the spring force, and the friction pads move out and come in contact with the outer drum. This causes it to turn. Both the shot type and the centrifugal pad type are automatic type clutches in that they require no external force other than the speed of the drive motor to engage them. Either type allows the motor to start turning while the load is disengaged. As I mentioned in our motor tape, part 1, a magnet will attract iron filings and make them stick together, as we see here. Now, if we take a loop of wire, pass a current through it, it will also act as a magnet, like this. If we take a coil, which has many loops of wire, like in this commercial coil, and connect it to an electric current, as we see here, we get a relatively strong magnetic field, which makes the filings stick together even more. We use this principle in the next type clutch, which is called a magnetic particle clutch. As we see in this picture, we have a rotor, which is shown here in blue. It's attached to one shaft, and we have an outer rotating member, shown in green, which encases this rotor, and yet doesn't touch it. This outer rotating member is attached to the outer shaft. The space in between the two is filled with magnetic particles, in other words, very fine iron filings. We have a coil of wire, shown here in orange, which is around the outer rotating member, but doesn't touch it. Now, when current is passed through the coil, it causes the magnetic particles to tend to solidify, and we transmit power from this section here to this section here. This particular unit is also used as a variable speed drive because by varying the amount of current, we can vary the magnetic field and can get more or less magnetic pull on those iron filings. Thus, as we desire more or less torque will be transmitted by the clutch. Next, we have the friction disc type clutch, and this we can see in its simplest form here. In this case, we have a metal disc on one side. Opposite it, we have another metal disc to which we attach a friction face and by some means press the two together. This then transmits force between the two shafts. This type clutch may be actuated in several different ways. It's frequently actuated with air. Now, here is an actual air-activated clutch. Here's the disc, and here's the friction pad. Its action can be seen better in this sketch. As you can see, when air comes in at this point, it moves the piston, shown in blue, forward, which presses this disc, also shown in blue, against this friction surface in orange. If this is the driving section, then when the two are pressed together, they both begin to turn. This section here with the metal disc is keyed to the shaft, while this purple section with the V-belt pulley turns free on this bearing until the disc is forced against this friction surface. Hydraulic pressure, that is, oil under pressure, could be used as the motivating force just as well. We can use an electric coil, which we've shown here in white, as a magnet, and pull the two surfaces together, as you can see in this sketch. In this case, we are using several discs together with a friction disc between each, and this allows us more clutching capacity in a smaller space. As with brakes, this is the primary reason for going to the multiple disc. Now here's an air type using the same multiple disc arrangement. In addition to this, we may have a jaw type clutch, which is operated by air, hydraulics, or electricity, and this in effect is similar to the first clutches we discussed. It is basically metal to metal contact, and there is, under normal usage, no slip between the two surfaces. As with the other jaw clutches, the units must be stopped to clutch in. Next would be the band type clutch. In this case, the clutch goes around the outside of a drum surface, very similar to the brake unit which we showed earlier. There are a number of different methods of doing this. One type which is frequently used is where we have a rubber tire, that is this section here, which is extended around the outside, to which air or hydraulic fluid is supplied. This, in turn, brings the friction surfaces in contact with the drum, as shown in this picture. This causes a clutching action between the drive pulley here and the driven drum here. In recent years, standard C-face clutch modules have been used in conjunction with standard C-face module units like this, which allows us to build up a system with a clutch or a brake by mounting it directly on the motor. Now, this greatly simplifies assembly of a unit in the field from stock parts. These are supplied as clutch units or brake units or a combination brake and clutch. They are available either air or electrically actuated, and for a complete discussion of C-face motors, see our motor tapes or our reducer tape. One final type clutch is termed oil in shear. This term is best understood if you will look at this metal block which we've placed upon a flat surface. This flat surface is covered with oil, and although the block moves relatively easy, if you try to move it rapidly, there is a resistance. This resistance is caused by the oil on the two surfaces, which tends to restrict movement. The principle is used in the oil in shear clutch. As you see in this sketch, two discs are shaped like this, with little rims on the edges. Then we have a tapered disc which fits up between the first two. When we turn this disc, we would normally have a rubbing action between them, except in this case, we have oil in between, and they never actually touch under normal usage. The oil which is on one is wiped off onto the other, and this wiping action, or as is more accurately called, shearing of the oil, transmits power from one to the other. While we have shown only one cone disc and two side discs, several discs are normally stacked side by side to increase the capacity. This particular unit can also be used as a type of variable speed drive. Depending upon the amount of pressure which is applied to press the disc together, we can transmit more or less power between the input and the output. This completes our discussion of brakes and clutches.